you can do it as 2.5 divided by 4 into 1000 millimeter, right. So, that will be how much? That will be 0.6, approximately 0.6 into 1000 millimeters, which will be approximately 600 millimeters. How much is 600 millimeters? So, if you change it in centimeters, it will be 30 centimeter, sorry 60 centimeter, which is approximately 2 feet, right. So, you want to make a specimen which is 2 feet thick. You remember the dimension of CT specimen. Dimension of CT specimen usually have a thick width of the specimen, which is W, and the W is usually 2 times of the thickness usually. So, that is the ratio which is maintained according to the standard. If you take a 3-point bend specimen, then there is another dimension, which is the distance between the 2 roller pins which are at the lower end of the specimen, that is called span length, okay, S. This S is usually 4 times of W, okay. So, now imagine you want to do the testing of this material, which has a fracture toughness of 100 MPa root meter, which is not abnormal, and a yield strength of 200 MPa, which is also very normal for steels, right. So, you usually get this ratio. So, you have to make a specimen which is 2 feet thick. So, what should be the dimension? W will be 4 feet. What will be the span length? So, that will be 16 feet, right. Can you imagine this kind of specimen which is 16 feet in span, right. So, even if you leave 0.5 W, 0.5 W there, so it will be 5 W, which will be 20 feet. So, 4 times longer than an average Indian will be 3 to 4 times longer than an average Indian this sample will be. So, you can test this kind of sample, and people have tested such big samples, but for that you probably have to do the whole casting of the steel to form this sample, and then who will carry it, and so there are a lot of problems, and doing this is not practical, right. So, why we are having this kind of situation? We are having this kind of situation because we have a parameter which only works when the material deforms in elastic manner. If it deforms in plastic manner, we do not have a real parameter which can describe the fracture toughness of the material, okay. And because of that reason, we cannot test materials which are deforming plastically, and this is very ironical, because we want materials to be ductile, we do not want materials to be brittle, we want material to be deformable, we want to make certain things, we want to give shapes to the material, we want to make car bodies, we want to make aircrafts, we want to make complicated shapes, like we want to make gears and shafts and what not, and we do not have a parameter which can work for this ductile materials. So, that is very ironical, and until recently, I mean in terms of other things, it was very recent when James Rice, and you must have heard this name before because I have used this name in this same course before. So, James Rice described a parameter for elastic plastic materials. This parameter is now used all over the world for fracture toughness measurement of the ductile materials, also for the polymers. So, polymers are very ductile, they are anything but brittle. I mean, you can have brittle polymers, but usually polymers are ductile, and you can use this parameter which was given by James Rice also at high temperature, also in dynamic loading. So, this parameter has got many applications in the field of fracture mechanics, and we will discuss about this. Now, the name of this parameter, unlike k, is j, which is very evident because it was given by James Rice. So, the name is j. And this j parameter is actually a line integral. Okay. So, a line integral, and this symbol is capital gamma, and gamma is the line along which this integral should be taken of some function. We will come to that function, but there is a function for which we take the integration, and that integration value gives you this parameter. Okay. The question is, why do we have to take this, and why integration and all those things? We will deal with all those questions. But before going there, we must understand something, that when there is a conservative field in physics, conservative fields usually are those fields which do not depend upon the path taken. So, they are usually dependent upon the initial and final position, and not on the path along which the curve goes. And so, one such field is gravitational field, and also electromagnetic radiation. So, if you take a mass which has its own gravitational field, and if you take a line integral along this field, and this line integral is usually taken in certain direction. So, you take it either clockwise or anti-clockwise. So, if you take anti-clockwise, the values is usually positive. If you take clockwise, it is negative. But if the line integral is circumscribing that mass, then this is the property of a conservative field in physics, that this closed line integral will give you a value of 0. Okay. This is similar to Kirchhoff's law in electricity, that at a node, if there are n number of currents coming in and going out, then of course, the number of currents coming in must be equal to the amount of, so not the number, the amount of current going out. So, why? Because we are conserving this, right. Similarly, it is a conservative field. So, if you take a line integral of that conservative field property, which in this case is gravitational force. So, if you take a line integral of that, it will be 0. This will not depend upon the path taken. So, you take a line integral at a distance of, let us say, 1 kilometer, or if you take a path at 10 kilometers, it will always be 0. It will also not depend upon the sign in this case, because even if you take even if you take clockwise, it will be 0, because the value is 0. Okay. But if you take a path or a line integral which is not closed, so if you take a path which is like this, then and now you take a anti-clockwise path, then this value will not be 0. It will have a finite value. Okay. It will have some value, x is the value. Along the same path, if you take opposite direction, it will have a negative x value. Okay. So, this is the property of a conservative field. This also happens when you take a line integral along a charge, electric charge. So, you will have Coulombic force, and if you take the integration, line integration around that, so you actually get that that equation, which is also represented in loop integral E with the electric field dl, and that is equal to the magnetic intensity. So, So, if you take the loop integral of electric field, then that is equal to the rate of change of magnetic flux. So, that is negative of ddt of magnetic flux. So, and that is true for electromagnetic radiation, because electric field will be changing in the magnetic field. This was found by Maxwell, I think. But before that, Faraday's law of integration was simply this. So, EDS is equal to 0. So, if you do not change the let me go to the, or we can describe it here only. So, if you have a wire through which current is passing, and then you take a magnet loop around it, and if you do not move it, nothing happens. But if you move this loop, then an electric current will be generated in this case also, which is induced current, okay, and that follows this law. So this is true in gravitational field, this is true in electrical field, this must also be true in the field of mechanics. And that was the idea which was used by James Rice to define his famous integration, which is called J integration or J integral. Okay. So, I will just introduce the J integral in this lecture, and we will talk about that in more detail in our next lecture. So, if you take a line integral of a conservative field around certain path, let us say that line, that force is F, it can be gravitational force, it can be electrical force, and then you have the position vector. So, F dr, if you take that line integral, and if it is a closed integral, then the value will be 0, unless you have a source or sink of energy. Okay. So, if I have source of energy or sink of energy, then that thing will not be 0. Okay. And that is the idea, that is the singularity. The source in our crack case is a singularity, and that singularity is our crack tip. Singularity mathematically means the point where you do not have the real correlations. So, you do not have mathematical equations there. So, according to theory of elasticity, the stresses are infinite, and so will be the strains, because in linear elasticity you will be following Hooke's law. So, stress will be related linearly to the strain, and if the stresses are going infinite, strain must also go infinity. But that does not happen in reality. What should happen in reality? We might have different equation in plasticity, but even those equations will not be valid exactly at the crack tip. Okay? And crack tip therefore becomes a singularity, and if you take a closed path around it, that will be describing the crack, the singularity, in a very unique way. And that is how the idea of J integral comes. But why this idea is so good? Why this idea is so beneficial that this can be used, and this is used in many of the applications? Okay? It is not able to describe the singularity. The J integral will not tell you what happens at the crack tip. So, then why are we using it? We are using it, and why this idea is very good is because it is path independent. Okay? That is the biggest and very advantageous virtue of this parameter, which makes it so good and so much applicable. The reason is this: we do not know what is happening at the crack tip, but we want to know. Something is happening at the crack tip, and if I take two different paths, why I cannot know anything at the crack tip? One thing, I do not have any equation. Another thing, I cannot measure anything at the crack tip. I do not have sophisticated tools which can measure the strains at the crack tip. if I put something, like if I put a strain gauge or something at the crack tip, then that strain gauge will be constraining the real material's behavior, right. If I really put something there, then that will be influencing the material's behavior at the crack tip, because my crack tip is very sharp and I putting anything will mean using or influencing the thing. So I can't do that. I can't do a real measurement at the crack tip, but I can measure things at a remote location, right. And this property is path independent. So if I take something here or there, the value is same. And so I take the integration at a remote location where I know for sure what is happening, where I can measure the strain values, where I can measure what is the force, what are the stresses. And if I know that value, I also know this value, because it is path independent, and that is what makes it so beautiful to use this idea in fracture toughness. Okay. So it is not necessary to have a circular path, you can take any path. Okay. So in a CT specimen, you can take a path which goes like this. You have to avoid the surface, you have to avoid the boundaries, because boundaries are difficult mathematically, okay, because there are a lot of things happening at the boundary, so we do not want those things. So we take this path, we take the cracked flanks, we ignore the crack tip, we take this, and this is my path. So whatever, if I know something at this path, must be true here at the crack tip, and that is how I can use this property. Okay. We must end this lecture here, and then I will tell you the equation of J integral in our next lecture. Thank you.